So one thing you need to know about mercury is that it's a horribly toxic reagent, and beyond that it's expensive to work with. So you might now be wondering why we do oxymercuration in the first place. So let me illustrate that for you. And again, the answer will come down to what happens if the electrophilic atom that gets attacked in the first place has a lone pair. Okay, we have this system right here. You're going to expose it to sulfuric acid and methanol. What's going to happen is I'm clearly going to add methyl ether across the double bond. I'm going to have a hydrogen get attacked, I'm going to make the secondary carbocation, and then I'm going to have methanol add, and then I'm going to deprotonate the protonated methyl ether. This is going to be my final product. Because the cation can be attacked from top or bottom, this will be a racemic mixture. I will make both of them, and lo and behold, that's what I expect to happen. However, bad things happen when you actually try to run this reaction, and so let's now walk through exactly where things go wrong. What we have here is the sulfuric acid drawn out, as you always should with any reagent that's over the arrow. The double bond attacks. Everything proceeds as you'd expect so far. You form a secondary carbocation, and again, everything is proceeding exactly as you'd expect. Now, naturally, what we want to have happen at this point is for the methanol, the solvent, to come in and add to make the protonated methyl ether, which then eventually gets converted into that material. That's what we want to have happen. Unfortunately, as soon as you form the secondary carbocation, there's the chance that one of these methyls slides over. And if that's what happens, then what you now get is a more stable tertiary carbocation, where the carbon over here on the left that originally had 3 methyls on it now is a more stable tertiary carbocation. And on the far side, we now have 2 methyls. So what happens here is, rather than the methanol solely attacking at the secondary position to give you the desired racemic mixture of methyl ethers, instead the rearrangement happens, and then the methanol attacks at the tertiary position, again leading to your protonated methyl ether, which then becomes deprotonated, and that then will be your final product, or at least one of your final products. You will at the very least form some of this intermediate. Once formed, of course, this methanol can be deprotonated by another molecule of methanol. Therefore, not only will you make at least some of the racemic mixture due to simple attack of methanol originally, you will also make this achiral methyl ether, which is presumably undesired. So it is the presence of this material right here that you don't want and that now you have to throw away that is the problem, and the reason why you would want a different set of conditions, a set of conditions that would avoid the formation of this product in the first place. And again, let me point out to you that the problem really resides here. You will, as soon as you make a full-on secondary carbocation, run the risk of a rearrangement, which would make the tertiary carbocation. This is lower in energy. You cannot prevent this from taking place entirely, which means that at least some of your material will be diverted away from what you want. That's why we need a different set of conditions. So let's draw those conditions out. So the whole point of this is that if you go through the oxymercuration reduction procedure, the 2-step procedure, then you never form a carbocation in the first place. And since you never form a carbocation in the first place, this is the only product that you make. If you are willing to run the risk of carbocation rearrangements, sulfuric acid is cheaper and less toxic. However, if you need to avoid carbocation rearrangements, then you cannot use sulfuric acid or any other acid, because all of them will go through the carbocation. Instead, you must use a reagent that has a pair of electrons as part of the electrophile. Because again, the key feature of this reaction is that your electrophilic reagent, the mercury here, has a pair of electrons, which means that when the double bond comes and attacks, the mercury itself will fire back its pair of electrons, and you will go through this sort of strange intermediate where the mercury is partially bound to both carbons. And though this molecule will then add in a Markovnikov-like fashion, which is to say, as though you had formed a secondary carbocation in the sense that that's where the methanol will now add, what you don't have is an actual secondary carbocation that can rearrange at any point. You have this species which is locked and stable. It will sit there until the nearby methanol can come by. Then the methanol will add in a Markovnikov-like fashion from the back side of the mercury, because the mercury is sitting on top, the methanol will add from the back side. You get the results of a Markovnikov addition of methanol, but you're going to come strictly to the secondary position, not attacking any rearranged products. You don't make a carbocation in the first place. What you have is this species, so it cannot rearrange. Therefore, you get the advantages of the Markovnikov addition, but you don't have the chances of rearrangements taking place. So the downside to using mercury is that you need to do 2 steps. It's horribly toxic. This stuff can totally kill you. Organomercury reagents are nasty. You don't want to work with them. But on the other hand, if you use the cheaper, safer reagent, which is sulfuric acid, then you run the risk of, unfortunately, making the wrong stuff. So that's why we have multiple tools in our toolbox, in our synthetic toolbox.